Hello everyone, welcome to our CeADAR and MB Tech Talk. For today's talk, we are going to have Dr. Pete Bunting from Aperture University, and Pete's going to talk about Global Mangrove Watch, which is a platform which uses AI to map global mangrove forest. I hand it over to you, Pete.
Great. Well, thank you very much, and thank you very much for everyone who's joined. Just to acknowledge some of my collaborators, whether that's Japanese Space Agency, JAXA, CeADAR, Wetlands International, Nature Conservancy, NASA, and University of Maryland, who we work with on various parts of this project. If you'd just like to go to the next slide. So just a bit of history for context. So this project was originally founded in 2011 as part of JAXA's Kyoto and Carbon initiative by my collaborators and colleagues, Orko Rosenquist and Richard Lucas. We then had a PhD student, Nathan Thomas, who did his PhD between 2013 and 2016. And his PhD was kind of developing some of the initial kind of methods and kind of background to what has then become the kind of methodologies we use. The first kind of publicly available maps were released in 2018. If you can just go back a slide. Yep. And then there was with Wetlands International and the Nature Conservancy, there was a portal, an online web portal, which was released in 2000. That's then resulted in the first State of the World's Mangrove report. And then since then, we've been updating some of the layers. So last year, we updated both the baseline and the change layers. And this year, we'll be updating the maps again. And we've also released near real-time mangrove loss alerts as well. So if we just go to the next slide. So the key kind of main aim kind of fits onto the Global Mangrove Alliance. And this is around kind of halting mangrove loss, enabling kind of mangrove restoration. So the Alliance has this aim of restoring half of the area of mangroves that have been lost and doubling the area of mangroves that's being protected. So if we go into the next slide, this then kind of links into our kind of technical aim, which is then how do we produce reliable, high quality mapping of mangrove extent and change, which allows those aims of kind of reducing the amount of mangrove loss. And that includes considering things like what drivers of change might be and identifying areas where mangrove restoration could occur. If we go to the next slide. So just some context, when we started all this work back in 2011, there were already a couple of mangrove maps available. There was the Geary et al. Map, which is from Landsat, which was dated around 2000. And then there was the World's Atlas of Mangroves from Mark Spalding, which was published in 2010. Both of these maps were dated around 2000, but they had various limitations in terms of kind of consistency of methodology, kind of the extent, and there was, particularly in the Geary products, there was some quite significant kind of misregistrations of the data, which limited the kind of use of these kind of existing data sets. So if we go to the next slide, this then led us to then split the analysis into two parts. First, create a new baseline. The original plan had been to kind of base it off the Geary map, but this, due to the various kind of data issues and things, it was considered that we would develop our own. So the first part of the talk will be about kind of the efforts we've done into developing kind of baseline maps for mangrove extent. And then the second part, where we use the JAXA L-band radar datasets to focus on looking at change in mangrove extent from that baseline. So if we go on to the next slide. So in terms of developing the baseline, there's been, well, 2 baselines developed and 3 developed. So the original baseline, the version 2 was the one that was released. Version 1 was an internal release where we only used the radar data to try and do a global mangrove extent, and it wasn't really good enough to be released. So version 2 was the first release. That was in 2018, as I said, and the baseline year is 2010. 2010 was chosen because this had the most complete coverage of the JAXA ALOS PALSAR data, and it had a resolution of 25 meters. We then, after the release of that map, various end users and also ourselves identified areas that were maybe poor in quality or areas that have been missed. And therefore, we did an update to the version 2 baseline, which was version 2.5. And then this year, we're working on a new baseline, which is version 4. Version 3 is a change layers that I'll come to. So we're currently working on a new global baseline, which is a resolution of 10 meters, and I'll show you some of the initial results of that during this talk. So if we go to the next slide. So in terms of how we developed the version 2 baseline, I thought it was perhaps useful to kind of go through some of the history, and you can see kind of the development of how we've ended up creating the layers and how the layers that are available are developed, and you'll see the kind of progress in terms of our thinking and methodologies. So this was work that was done from about 2016 to 2018. And there was 2 key data sets in here. There's the ALOS PALSAR L-band radar data, and there's a Landsat composite. So this was a composite of 15,000 individual Landsat scenes. And these were cut up into 118 different projects, which basically divided the world. And all the processing was done individually on these projects. So training data for the random forest classifiers and all the different analysis in terms of the classifications and QA and everything was done on a project by project basis. And then those projects were merged to produce the map. The analysis was split where we did 2 different classifications. The first was just using the radar data on its own. And this was actually kind of the GMW version 1 map that was never released. And then basically we did a refinement within that extent because it generally overclassified kind of the mangrove extent. So we then did another classification within that area using Landsat to basically refine the area that we were mapping. One of the reasons that we did that is that the Landsat composite was probably kind of 98% complete. There were kind of areas, particularly places like Niger Delta and things like that, which had extremely high cloud cover, where basically Landsat data in 2010 is not an optimal year. But given the fact we were using that baseline data due to the JAXA data we were using what we had. So there were areas where there was no Landsat data coverage for that year. So therefore that was only based on the radar classification. So we kind of had these kind of 2 classification steps that went into producing that product. So if we skip on to the next slide. So from that, there was a whole number of areas that were found that areas we could improve. So there were some artifacts from the Landsat 7 LCSF striping effects that were in the product in some areas, particularly in areas of high cloud cover. So in some areas in the Niger Delta, Papua New Guinea and places like that. There were some areas, so the classification is performed within an area in a mask that we call a mangrove habitat mask. So we only look for mangroves within those regions. And there were some areas, and there's an image at the bottom of the scene here where you can see an area in Florida where the habitat mask was perhaps too tightly constrained, and therefore it wasn't capturing the full extent of mangroves because of the errors in the habitat mask. So there was a few errors like that that had been identified. So we were correcting those. And there were some other areas where the classifiers just hadn't worked particularly well. In that context, these areas, the image in the bottom left, all those areas in red were areas that were then deemed as being poor quality and would be remapped as part of the kind of version 2.5 update. So if we go on to the next slide. So within those regions, given that we'd used essentially the best available data for 2010 that we could in the original version 2 map, we then therefore needed to use a different data set. And in this context, what we did is we used Sentinel-2, and we used basically the best available Sentinel-2 scenes we could get from the time series, and didn't worry about the fact that it was a different date at this point. So we downloaded 11,000 Sentinel-2 scenes that were atmospheric corrected and cloud masked. And then in those regions, there were about 50,000 reference points, 55,000 reference points that were identified for mangroves, and another 50,000 for non-mangroves. Once we intersected that with the kind of 11,000 scenes, we ended up with a larger kind of number of kind of reference samples that we could use to train the classifiers. And we then split that 4.5 million reference samples. One of those numbers, the 4.4 million is correct, but 56 is too small to make 45. Anyway, so we used the 4.4 million samples to basically train 100 XGBoost classifiers. So the logic here was the fact that we probably had too much data for the hardware we're running on at the time to train a single global model. The areas are kind of, there's some variation in the areas that we were looking at. So basically we split this down and trained 100 different XGBoost models using random subsets of all the training data. So essentially putting kind of another ensemble of classifiers together. These were then applied to each of the 11,000 scenes independently. So we took each of the 11,000 scenes, some of those will have holes due to cloud cover and things like that in them, and we applied all 100 classifiers. So we essentially ended up 100 classifications of mangroves, not mangroves, for the 11,000 scenes. Those were all then merged together, both in terms of overlapping regions of the individual Sentinel-2 acquisitions, but also the 100 classifications. And basically that was summarized and given basically into a probability value of the probability of a pixel being mangroves or not mangroves, that was then thresholded to give a mangrove, not mangrove mask for the areas of interest. The resulting mask kind of map of mangroves, not mangroves for these regions was of a date somewhere between about 2015 and 2019. To get that back to our 2010 baseline, we did a change detection process, which is the same change detection that we use for doing the different change layers and the GMW layers. So I will come on to that later. But essentially we did a change detection from that these remapped areas using Sentinel-2, using the radar data from 2010 to get that back to a 2010 baseline year. And then that was then merged with the version 2 layers for the other regions that weren't updated. So that gave this version 2.5. So if we just skip on to the next slide. In terms of accuracy, for the areas that we remapped, the accuracy of the old version 2 layers was about 82%. In those regions that we remapped, so this isn't a kind of global accuracy assessment, this is just focused on the areas that we remapped, that increased the accuracy to about 95%. In these few examples, you can see the top right there, this is an example of where we had the kind of LCCS, sorry, the SLC striping in the version 2, which you can no longer see. And you can see that having used the Sentinel-2, we've probably got a bit of better definition on some of the river channels and things like that. The bottom left, this is an area in Florida, which I already showed, where we'd cut the habitat mask too tightly. And then in the bottom right, this is an example from Colombia, where there was an area that just hadn't been mapped in the old version 2 layer. It just wasn't in the habitat mask at all, and it wasn't in Geary's map and things like that. So that was something where an end user of the map kind of contacted us and said this area has been missed, and we were able to then add it into the next maps. So if we go on to the next slide. So moving on to what we're now working on. So this is work that's currently ongoing. So the portal has now been available online, and we've kind of an increasing number of end users of the data sets of the portal. And one thing that's becoming apparent is the kind of, I guess, an increase in interest and in kind of feedback from end users that they want maps that are kind of increasingly locally relevant. So while they want global coverage, they also want to be able to use the maps for quite local area studies. So kind of a single bay or kind of a single area that they're looking for restoration. And that means we need maps which are higher spatial resolution, and we also need higher degree of basically accuracy at that local scale compared to the existing maps. Now, we're also trying to do that at a global scale as well, which kind of represents challenges. Therefore, to kind of like basically achieve that, what we've done is to say, right, we will create a new global baseline for mangrove extent. That'll be based on Sentinel-2 with a resolution of 10 meters. The old maps were a resolution of 25 meters, and we'll have a new baseline year of 2020. So in terms of the kind of methodology we're using, we've used the kind of version 3 of the GMW basically to automatically define a global set of reference points. Those reference points total about 5 million between the classes mangroves, water, and other terrestrial. We've then done some analysis to using the Sentinel-2 reflectance. We've then done some outlier analysis to find ones which are likely to be or could be errors, as in kind of they're misassigned, which we've then kind of manually kind of QA'd and visually checked. And we're now in a process of basically going through this whole processing chain in an iterative basis of reducing a map and then kind of looking at areas and finding areas that maybe need improvement, and then going through and editing the training data or editing the QA in the map in some other way, doing some improvements, and then rerunning the analysis. The Sentinel-2 data we're using has been provided by Vito in Luxembourg as part of their analysis they were doing for the ESA World Cover kind of project. So this has meant that we're using, rather than using the individual scenes that we used in version 2.5, we're using temporal summaries, and I'll come on to what that looks like. We then have been continue using XGBoost as our classifier, but here we've been able to kind of make use of the GPU to train a single global model and do the kind of parameter optimization on the whole data set and do feature selection on the whole data set. So that's meant that we've been able to basically train a global model with several million reference samples being used. The other step we do is that we take each of the 36,000 Sentinel-2 scenes and we do a transfer learning. So we take that global model and then we take the some reference samples around that scene or within that scene and within a neighboring area up to about 2 degrees away, and basically take up to another 10,000 points per class to kind of locally optimize the global model to apply for each of the scenes. Once we've done that and applied it to all 36,000 scenes, we then reproject those, because they're all in UTM, into WGS-ESC4 and then merge them all to create a single map. So if we go on to the next slide. So in terms of kind of like what that looks like in terms of the comparison to the version 2.5, the big difference with the Sentinel-2 data is we're using these temporal summaries. So that basically means that we're taking all of the acquisitions for 2020, processed to 10 meters, and then taking the percentiles of the reflectance bands. So taking the 10th, the 50th, the median, and the 90th percentile. So that's hopefully capturing some of the kind of temporal aspect to the data. So you're getting some idea of what the reflectance is of the pixel, but also how that pixel is varied through the year. And then we also do that for a number of different indices like NDVI, NDWI, etc. Another variable that we add into the classifier is we actually put lat long into the global model. So therefore, hopefully XGBoost is also able to do some local optimization of itself to learn some of the differences in the way that mangroves appear kind of across the globe. So that's kind of the data set that goes into the model. And then the second kind of significant difference is, rather than kind of splitting out all of the subsampling, all of the training data, reference data, and creating these 100 XGBoost models that we then apply as an ensemble to each of the individual scenes, we create this single global model and then transfer learn to optimize to each of the local areas. So that's the kind of main kind of, I guess, methodological developments or improvements or differences between the kind of what we did in version 2.5 to what we're now doing in version 4. So if we go on to the next slide. One of the challenges that we have with this data set is that we are finding that there's quite a lot of areas that are being identified by mangroves by the new classifier that haven't been identified in mangroves in any of the other kind of global or regional maps of mangroves. Now, a lot of those are mangroves, but an awful lot of them, well, not an awful lot, but there's also a number of them that are not mangroves. So what we've been doing is to use the existing global products and kind of where there are kind of local, national or maps, say like Mexico, we've been using those basically to confirm that some of these features are mangroves. And that then splits the kind of features that have been mapped into confirmed mangroves and unconfirmed mangroves. And you can see in the images on the right-hand side here, the green ones are areas that have been correspond with some of the existing global maps or our training points. And we can use those, and they've been confirmed as being mangroves. The areas in red are areas that are in this kind of unconfirmed layer. And some of these features are really quite small, as in like 2 or 3 pixels or single pixel features. So there's about 500,000 of these features that are in this unconfirmed layer. And basically the challenge is how many of those features are really mangroves and how many are not. So at the moment, the main way in which we're dealing that is to visually kind of go through and check the data set and basically put eyeballs on the data and confirm things as being mangroves. And you can see in the bottom left there, that's an area where the areas in red are pretty much all going to be mangroves. They're all on the coast, they're all kind of quite clear, and it's probably pretty safe to kind of pull those across and call those mangroves. So a quick check against the Sentinel-2 data or against kind of Google Earth imagery, Bing imagery, we can kind of pull those in and confirm them as mangroves. The example in the top right there is where we're in an area where there's kind of aquaculture ponds, and there's a lot more kind of complex kind of land use going on in that area. And that's where it becomes a lot more difficult to confirm what is mangroves and what is not mangroves. Even looking at the kind of higher resolution Google Earth or Bing imagery, it can be pretty difficult to tell whether some of these areas are really mangroves or whether they're just spectrally similar to mangroves. And I think my judgment here is that we're probably getting to the limit of what kind of a single pixel based classifier is able to achieve, because we're still looking at each pixel independently, and we probably need to start putting in some context if we're going to kind of automate some of this in the future. I have project deadlines, so I'm not able to kind of put time right now into kind of developing this on further. So basically we're doing a kind of this visual based analysis to confirm kind of mangrove features as much as we can. But I think in the future, we'll probably end up going to some, or at least investigating using some sort of convolutional neural network or similar to try and give us a kind of a context, the classifier context around features rather than just pixels on its own. But that's kind of, that'll probably end up being version 5 of the Global Mangrove Watch or something like that in a few years' time. So if we go on to the next slide, just to give you some comparison of kind of how the version 4 and version 5 maps compare. The top left is an example where nothing was actually in the version 3 maps. And nothing is in the Geary map and things like that. So that's an area that we still occasionally find where actually there were no mangroves mapped in the earlier maps. In the top right there, that's one of the examples I showed on the previous slide, where we've now confirmed these areas as mangroves. So it's a more complete map. The bottom left, this is an area in Northern Australia, Kakadu National Park, East Alligator River. And what you can see there is actually, this is pretty representative of the majority of the map, where actually it looks pretty similar. When you start looking at the details, what you see is that the we've captured more of the small finer detail because we're at the higher resolution. And we've been able to capture kind of more of the mangroves going inland. So the rivers, the kind of finer features going up the rivers are better captured and things like that. But given the old maps had a high accuracy into the 90s, it's not surprising that there's a strong correspondence between the kind of majority of those layers. So if we kind of switch to the next slide. So going on then, so that's how we've been developing the baseline maps. And those baselines have then been used to do change away from that baseline to then look at how mangroves are changing globally. And this is based on the Japanese Space Agency's L-band radar missions. So there's 3 missions that have been launched to date. There's the JRS-1 data, and we have Mosaic products for 1996. The ALOS PALSAR mission, which gave data from 2007 to 2010. And then ALOS-2 PALSAR-2, which has given data from 2015 to present. In the version 3 maps that are currently publicly available, that's been only processed to 2020. We have data for up to 2022, and when we release the version 4 change layers, they will include up to 2022. So basically, what we're doing here is we use the baseline map that we've already developed. So for version 3, that was the version 2.5 baseline. We then define regions which are not mangroves, which could be mangroves. So low backscatter regions, basically areas of kind of neighboring water bodies and things like that. So kind of a contextual layer. And then essentially we look for kind of areas that were mangroves in our 2010 baseline and are now mangroves in any of the other years, and things that were mangroves in, were not mangroves in 2010 and are mangroves in some of the other years. And I'll go on to look at how we do that. One of the advantages of using the radar data over the optical is the fact that the radar data sees through the cloud. So we easily get an acquisition everywhere, every year. So it has that, well, everywhere that an image, a data set is acquired. So it has that advantage. And really what the radar is seeing is the structure of the vegetation. So rather than the optical, which is seeing how much light is reflected off the surface, the radar data is sensitive to the 3-dimensional structure. So when we're looking at change, what we're looking for is basically a change in the 3-dimensional structure of the landscape. So if you've got an area of mangroves that gets deforested, then we're looking for an area that did have a vertical structure going to an area that didn't, and then vice versa, an area that wasn't mangroves, had no vertical structure or little vertical structure, and then it converts into something with trees growing out of it, and therefore it has a vertical structure. So if we go to the next slide, I can show you kind of what that essentially looks like in the satellite imagery, in the radar imagery. So in the top right here is some examples where the 1996 data is represented in the red band. The 2010 data is in the green band, and then blue is represented by 2020. So where you see areas of red, like in say like the top right image, which is an area in French Guiana, what you have there is an area that had high backscatter in 1996, so there was vertical structure, and then it had low backscatter, it was an area of water in 2010 and 2020. And the same on kind of the top one on the top left, kind of A, which has got an area in the Sundra Barns where you can see that kind of mangroves are being eroded away. You're seeing that kind of that transition, and the C is an area in Sulawesi in Indonesia. Counter to that is when we get a growth in mangroves. So in D, in the bottom right there, The areas in blue had a high backscatter in 2020 and low backscatters in the other years. And this is an example of where you're seeing mangroves basically expand, in this case, out to sea. So we make this kind of key assumption that basically where you end up with kind of this change in backscatter, where mangroves are changing, we're getting this change in backscatter, i.e. a change in structure. The situation where that can fall down is primarily where you end up with like coastal developments. So say if you get a new port or airport or something like that being built into the coastal zone, basically that if it's in a mangrove region, that can end up getting captured as potential mangrove change. To remove those, we've kind of manually kind of QA'd them out. It's a pretty rare for that to happen, for those kind of changes to happen, and most of them are in kind of China and northern Vietnam, and there's a little bit in kind of in the kind of area around Malaysia and Singapore, but as a kind of globally at scales looking at that, it's a pretty rare occurrence. So these assumptions hold kind of the majority of the time. If we can just go to the next slide. So the other thing that we have this baseline that says, where is mangroves? We need the kind of opposite layer, which is areas that could be mangroves but weren't in 2010. And in these figures here, these are the areas that are shown in blue. So to define these regions, we need areas which are kind of low in elevation. They need to be kind of low in terms of their backscatter at kind of at some point in the other years, but they also need to have increased at backscatter in some point in the time series. So i.e. they need to have had some change going through the time series for us to look at them. And they need to be within a kind of a distance of an area that we know is mangroves already. So one of the limitations of this is that if you suddenly end up with a new mangrove area that appears at a different date that is in nowhere near anything that's been mapped in the baseline, we won't be picking it up. But again, it's probably a very small number of cases where that would occur. So basically, that gives us these two classes, kind of where mangroves are in 2010 and areas which are low backscatter in 2010, i.e. a relatively smooth surface with no or little three-dimensional structure that could be mangroves at any of the other dates. And it's within these two regions that we then do the change detection. So if we go on to the next slide. So the change detection approach we call a map to image approach. So what we're doing is we look at each class in turn, and essentially we make the assumption that change is outliers. So if you're looking at a loss in mangroves, if you take the backscatter, if you look at the histogram, the backscatter for all the regions that you think are mangroves, so mangroves in 2010, and look at where the backscatter is low, so you end up with like a tail to the histogram, i.e. outliers. These are the regions that are likely to have been lost compared to that 2010 baseline. So you can see in the example on the left-hand side here, you've got an area in the Sunshbans that I think I showed earlier, where you've got the image in 2010 and 2020. And what you can see is that you've actually got kind of the ends of the mangroves, the southern ends are eroding. And you can see the histogram here where you've actually got the red line, which is the threshold we use in this particular area to basically separate mangrove areas, which is the kind of majority of the histogram, from non-mangrove areas, which are these outliers. And essentially we do the reverse for finding areas of gain, where we've got these blue areas that we defined on the previous slide, which are low backscatter areas in 2010. What we assume again is that kind of gains in mangroves is relatively rare. So therefore we're looking at outliers. So we've got the majority of the histogram is going to be kind of low backscatter regions, and we're going to get an outlier of higher backscatter areas where basically areas have turned into mangroves. And you can see this example in Venezuela on the right-hand side here, where we've entered this area that's gained in mangroves between 2010 and 2020. So if we go on to the next slide. When we did the original version 2 mapping, we just took the 2010 baseline and we did that change analysis to all of the to each of the other years, and then did some temporal filtering, did some QA, and that was the maps. For version 3, we took a slightly different approach where we did the first step was to do the 2010 baseline and do that to all the other years. But we added another step, which this animation at the bottom there showing, where we took each of the other years then that we had as a baseline, and then did the change detection against all the other years. So essentially we ended up with 10 mangrove maps for each year, which we then took the majority of to give the kind of result, to give the kind of final mangrove map. So there was like an ensemble of maps produced from the change detection, which we then just took the majority result from. So that helped to kind of filter out a bit of noise and things like that in the results. So if we go on to the next slide. One of the problems that we had with the L-band radar data is that was a misregistration within the data. It could have, in some areas, it was up to about 4 pixels. And this was actually exaggerated because JAXA identified that there was an error through some of the feedback that we and others had given in about 2017. And therefore, they started to correct this error. So kind of in 2020, they'd actually corrected the error. But of course, our baseline maps are all on the 2010 baseline. So therefore, to avoid getting quite significant biases in the data, we had to apply some automatic image registration stuff to the JAXA mosaics. But this does have some consequences for how we recommend in which the current maps to be used, and the kind of level of uncertainty we have in the estimates of kind of global mangrove change. JAXA are reprocessing the whole archive. That I have most of the data already reprocessed from JAXA, and later next month I'll have all of the different layers. I think I'm just waiting for 2 more years. 2 more years to be reprocessed. So when we do the version 4, this problem will have gone away. So we go to the next slide. So this just shows some of the results where you kind of steps through the time series. I think the kind of take-home message is that kind of like where you have kind of large changes in mangrove extents, kind of those are picked up really quite well. However, if you're looking at kind of small features, and particularly looking at small areas, you can still find that there's some artifacts from that kind of misregistration in the JAXA data, because while the re-registering the data with the automatic tie point generation significantly improved things, it didn't remove that misregistration in the kind of whole data set. So there is some caution that's needed kind of when you're looking at kind of small patch sizes. I think in terms of our main focus in terms of dealing with that misregistration was try and remove bias. So therefore kind of the trends and everything would be reliable, even though our uncertainties may be relatively large. So if we go on to the next slide. So just to give you some accuracy, this is actually focused just on the change detection. I guess the main ones here to focus on are the change categories. So mangroves going to not mangroves and not mangroves going to mangroves. And these are kind of both around 60%. And that's basically because of the impact of that misregistration within the JAXA data sets. So if we go on to the next slide. So just some broad numbers. We mapped 152,000 square kilometers of mangroves in 96. And that's increased to, well, so that was decreasing through the time series. And kind of up until about kind of 2015, that was kind of decreasing quite significantly, or more significantly, I guess. But after, in the kind of last few years of the time series, we saw that basically the rate of mangrove loss slowed a bit. And that gives us kind of a total net loss between 96 and 2013 of about 3.4%, or about 5,000 square kilometers. Of course, the caveat here is that there is, of course, quite a lot of loss and kind of a certain amount of gain as well. So kind of that's not just the amounts lost, that's the kind of net change. And something else to highlight is because of that misregistration, some of the kind of confidence intervals around our extents are relatively large within this version. So you can see in the table here those confidence intervals. So that is something just to bear in mind with this current version of the dataset. So if we go on to the next slide. So things that we're working on in terms of what improvements will be made to the change for the version 4. We're going to be have a much better coverage of mangroves, as I showed you in some of the comparisons between version 3 and version 4. We're fixing a lot of those issues. The fact that JAXA have reprocessed all the data and that solves a lot of the misregistration will really help to reduce the uncertainties around the change. In terms of methodology, the plan is to follow the same methodology, or we are following the same methodology to be used in version 3. The only kind of addition will be going to introduce some optical data just to do kind of veg, non-veg masks for what we're counting as change in mangroves to try and remove some of this kind of coastal development areas. And I guess that particularly that will kind of impact areas maybe in China and kind of northern Vietnam. Although those areas were kind of the vast majority of those areas were manually removed anyway. So we go to the next slide. So just so you're aware, the data sets are all available. You can go onto the Global Mangrove Watch portal, where you can view the data and you can query it and get statistics for countries or your areas of interest. The data are all available to download. So JAXA have a site where you can download the raster data. The UN Ocean Data Viewer, the vector data sets are available, and the whole thing, as published, is available for download on Zenodo. If you just go to the next slide, one of the things that we've been working on recently, and I'm not going to go, I have some more slides, but I probably don't have time to go through all of those, is we've also been looking at improving the kind of local relevance of the changes. And that's led us to basically develop a near real time monitoring system where we're mapping mangrove losses with every month. So on the portal, you get monthly alerts of mangrove losses. So if we just skip on a slide, skip on another slide, we'll skip some slides here, I think. Skip on another slide, I'll skip them going through them. If you skip. Yeah, skip. If you just go back a slide, back one more. Yeah, so this is a kind of example of where we're kind of the kind of changes we're picking up through these monthly loss alerts. So basically with their points, and each point represents a 20 by 20 meter area on the ground. And this particular area, what you're seeing here is the 2018 planet imagery in D, and then kind of the 2022 planet imagery. And you can see there's an area of dieback there. And this was due to basically storm damage from a cyclone. So if we skip on another slide, you can see here that we end up with, this is the kind of cyclone tracks for for Africa, basically, and they're all in this kind of area of the Mozambique Channel. And this particular large cyclone caused quite a lot of damage in the mangroves, which is really kind of, I guess, we've seen a lot of alerts being produced. So if you skip on a slide, skip on. So this is an example of kind of how these alerts are being used. With Wetlands International, that we work with their field teams, or kind of in Guinea-Bissau, which is where this example was. But also we have got examples from Kenya as well, where basically we see alerts occurring in a month, and then basically staff are able to go out and have a look at what is occurring. In this particular case, we saw that there were a number of alerts being produced within this region of Guinea-Bissau, and Wetlands International staff were able to go out and have a look. And what you were seeing there is a dam being built, and this particular area is being converted for rice cultivation, basically for food security. So it's a government project, which means that in this particular case, we're not able to do anything about it, this particular mangrove loss, but it could be in the future that kind of like, hopefully there'll be areas where we find alerts and we'll find them in time to be able to, I guess, alter kind of the kind of trajectory of mangrove loss using those alerts. So if you scroll, you go to the next slide. Yeah, that one. If you just go back. Sorry, forward, next slide. So at the moment, the publication that we did that came out in April this year was just focused on Africa. So we're providing the alerts for the whole of Africa, but we've also providing on the portal the alerts for some other areas like Mexico, Ecuador, French Guiana, Suriname, Guyana, Bangladesh, Myanmar, and some parts of Indonesia, in this case Borneo and Sulawesi. So the alerts are being produced there. We are going to be expanding the alerts to include Thailand next month, and we are still waiting on funding, but the plan is, all being well, that we can expand the alert system globally in 2024. So it's worth being aware that if you are looking at mangrove change, in addition to the kind of global extent products, there's also these monthly alert products, and the alerts are monthly from January 2019. So we've kind of processed it historically as well, and they're being updated on a monthly basis and available on the Global Mangrove Watch portal as well. So we can just go on to the next slide. So where we're going, I guess, in the future, most of my time and effort at the moment is on the version 4, finishing the version 4 baseline and producing the change layers that will be released later this year. I guess in the medium term, when we come to do look at baseline mapping again in the future, as I said, probably we'll end up looking at some sort of CNN-based approach. We would like to move the extent mapping away from our compute systems here in Aberystwyth to something like a cloud-based solution. For the alerts, we're using the Microsoft Planetary computer, and I guess we will probably move to that platform. We'd like to expand the kind of temporal resolution and fill some of the time gaps using the Landsat archive of the changes going back in time. Ideally, it'd be nice to get back to 1990 in that way and things like that. And the other side of it is also to try and go beyond just mapping extent of mangroves, but also try to look at kind of condition. And this figure on the right-hand side, there is some work we did in Australia a few years ago, where we looked at kind of creating a canopy cover product from Landsat and looking at how that canopy cover product changed through the Landsat archive, and that enabled you to pick out details like dieback events, but also the impacts of cyclones and recovery from cyclones and things like that. And I think expanding that globally is something else that's would be good to do as well. So I've finished talking, so if there's any questions, I'm happy to take them.
Yes, thank you for your talk. I have a few questions. Do you hear me?
Yes, yeah.
Yeah, I am mostly interested how you created a training data set here, and how do you assess how many points in a training data set you need to have reliable